Hello and welcome to the 12th session of the LSSTC Data Science Fellowship Program, our second ever virtual session. We're glad that you are able to join us once again through this new and virtual format. This session, as we will dig into over the course of lectures that will occur over the next week, is focused on data visualization. And there are many reasons why data visualization is important and an essential tool for the modern data scientist. And in particular, we'll be focusing on how data visualizations and the creation of things like plots, figures, and slides are an essential ingredient in scientific communication. And we will also be talking about cases where data visualization can lead to discovery or a better understanding of the data set that you are dealing with. So all of these and more topics will be what's covered during the lectures that occur this week. As is typically the case, I will be providing an introductory lecture right now to sort of set up some of the topics that we'll cover in more depth. And in particular today, what I'm going to be talking about is building salience in scientific figures. So without further ado, let's get into it. Before we really jump in, we're just going to ask you for a moment to provide me with some time for a short preamble. So during the previous session, session 11 of the DSFP, where we focused on image processing, implicit in all of our discussions about measuring PSFs, CCD detectors, how do you estimate astrometry from an image, etc., was the importance of data processing pipelines. And the importance of these pipelines that is implicit in all of those discussions needs to be understood with good reason, because the Vera-C-Rubin Observatory ultimately will observe 37 billion sources, each one of those sources with about 1,000 observations taken over the course of a decade. So we're talking about databases that are going to have tens of trillions of rows, and just an overwhelming amount of information for everything that's observed by the Rubin Observatory. And so pipelines are going to be essential to make sure that everything is sort of treated and processed and measured in a uniform way. So even if you were to collect together the largest group of astronomers and even, say, volunteer astronomers from citizen science websites and things like that, and you pulled all of them together and asked them to look at everything that was observed by the Rubin Observatory, you would fall woefully short. And this is why pipelines are so incredibly important. And as good data scientists, we should all strive to develop software solutions that are going to produce reproducible analyses of our data. And as we teach in the DSFP, this means things like building software packages with version control, whether that be Git and GitHub or something else. Working on things like continuous integration so that we know that any changes that we might make to the software still run appropriately no matter what platform you're running. And then sort of at the highest level, we should even be doing things like creating containers that don't just contain the software itself, but contain sort of a full build, including all of the packages that the software relies on in order to always reproduce exactly the same analysis no matter who's running it on any computer in the world, right? And all of this is part of building an exquisite and excellent pipeline. But it is important to remember that pipelines can only accomplish the task they have been asked to do. So essentially, a pipeline says, this is our algorithmic procedure for dealing with all of the data. And once that algorithm is done, you sort of get out the output that you expect. Okay? So allow me a time for a short anecdote here. Towards the end of 2007, there was a stripped envelope star that exploded as a Type 1b supernova. This was called Supernova 2007 UY. And it was in a nearby galaxy, NGC 2770. And you can actually see beautiful spiral arms in the image on the right of your screen, which is an optical UV image. And the supernova itself is a very bright source, which has been circled in white. Okay? And given the proximity of this particular supernova, observations with the NASA SWIFT satellite were triggered to see if any X-rays could be detected. And in the image on the left, you'll see an X-ray image, which has far fewer sources because the X-ray sky is a lot fainter than the UV optical sky. But you will see that the supernova in question was detected by the SWIFT satellite. So there is X-ray emission from this particular supernova. Now, NASA has a high energy research archive team, and they essentially have built all the tools you might need. So there's software to reduce images, software to measure fluxes, software to basically stitch all of this together into a nice pipeline so that anyone working with SWIFT data, if they know the position of their source, can build a pipeline and extract an X-ray light curve with the full luminosity as a function of time. And that's great. So for this example of Supernova 2007 UY, you could build that pipeline, you could hit go, you'd get a nice light curve, and you could be on your merry way, sticking that into some figure that you put into a paper on this unusual nearby supernova. Now, of course, if you did build such a pipeline and just hit go, you would have missed this. Okay? Here's the same galaxy, and you can see Supernova 2007 UY highlighted again with the white circles. But what you'll notice, the thing that's starkly different in this particular image, is that Supernova 2008-D exploded about a month after Supernova 2007 UY. And not only did it explode a month after 2007 UY, it happened to explode at a time when the SWIFT satellite was looking at the telescope. So you can see in this new X-ray image that was taken a few weeks after the first one of 2007 UY, there's a bright, bright, bright source. In fact, there are no other sources that are detected because this source is so bright in the X-rays. It completely dominates anything that you see. And this essentially occurred because 2008-D was imaged literally seconds after the star exploded. This is the definition of serendipity. The point of those observations was to look at this other supernova that was slowly evolving, and instead, we happened to find a supernova at the moment of birth. Okay, but that discovery would not have happened if Ido Berger and Alicia Soderberg had not been looking at the SWIFT data itself. I contend that 2008-D is actually one of the most important supernova discoveries from the past 2 decades. There literally are no other observations of any other supernova ever like the X-ray observations that were obtained for 2008-D. And they provide a whole bunch of information about the physics of that particular star and its explosion. Okay. So, what's the upside of this anecdote? Pipelines are wonderful, they are necessary. In many cases, they can even be lifesavers because they prevent you from sort of having to do repetitive tasks again and again and again and again. But one thing I want to impress upon all of you during this talk and throughout the course of this session is that there is no replacement for looking at the data. Obviously, in the Rubin Observatory era, we will not be able to look at everything, as I said before, but still, looking at the data is an essential ingredient in being an astronomer, even an astrodata scientist that does most of their analysis via large, complex software pipelines. Okay? In other words, following on the theme of the DSFP, those that worry about the data look at the data. And I should add that the most vexing problem of my career was actually solved by looking at the data. So I won't go into this in great detail or for a very long amount of time, but in short, I was trying to build a machine learning model that would identify stars in astronomical images. And I was using spectra from the Sloan Digital Sky Survey, which has literally millions of spectra of galaxies and millions of spectra of stars as a training set. So this is sort of an ideal way to build out such a machine learning model. And I had this really weird feature where all of the galaxies, many of the galaxies, were being misclassified at about 20.5 magnitudes. At 19th magnitude, they were fine. At 21st magnitude, they were fine. But at about 20.5, a lot of them were being misclassified, and I couldn't understand what was going on. I asked several machine learning experts that I knew. I asked all kinds of galaxy experts because I don't know a lot about galaxies. I asked experts about the Sloan Digital Sky Survey. No one had an answer that made sense. I tried all kinds of different solutions, none of them really correcting the problem, until one day I said, okay, I'm just going to look at thousands of images of Sloan galaxies and stars to try to figure out what's going on here. And here's a short rogues gallery that essentially provides the answer for this particular problem that was plaguing me for months. And that is that Sloan was very interested in taking spectra of red galaxies. And it turns out that if you take a faint red star and you put it very close to another star, another faint star, from an imaging pipeline, that will then look like an extended source or a galaxy. And so Sloan took all kinds of spectra of these things, and you can see examples here. These all look like extended sources, but they're blended stars. And so the spectra labeled these sources as stars, even though photometrically it's nearly impossible at the resolution of Sloan or other typical ground-based surveys to determine that these are two different sources that are very, very close to each other. And so that is how looking at the data actually solved one of the most difficult problems that I was encountered with in my career. All right, so now let us move on to the introduction. So as I said at the top, session 12 focuses on data visualization. Informally, I am hoping that over the course of the lectures that happen this week, we can answer the question, what is the best way to communicate or discover the most important features within a data set? So as scientists, we primarily communicate via three mediums. So we use text, which is in the form of papers, or in some cases also things like technical reports. And we all have experience, right, as we've come up through school, writing lots and lots of text. We also do this via speaking. So this is something like a talk or a lecture. And finally, the sort of third and final main avenue of communication is visualization, including figures, which are be put into things like papers or talks or slides that will become the backdrop for what we're trying to communicate during talks. As human beings, we communicate via stories. So it seems plainly clear to me that if you are writing a paper or you are giving a talk, you are telling a story. And that story is well constructed with a beginning, middle, and end. Right? The standard paper starts with an abstract, then there is some sort of introduction, some notes about the data and analysis, perhaps a results section, and then finally a conclusions, right? Introduction, beginning, analysis, results, middle, conclusions, end. If you're building a visualization, you should do the same thing. You should also be telling a story. This is an idea we'll come to a lot over the course of this week, so I'm not going to harp on it for too long right now. So that brings me to the first breakout problem of this lecture. I want you to tell me what is the story of this figure. And I'll wait a second so you can take a look and think about it. Okay. That's enough. My eyes. This figure hurts my eyes. That visualization has a whole bunch of problems. And a lot of them come from the basic construction, the use of the jet color map, the overlapping symbols, the lack of visual boundaries, the fact that you have no sense of what the underlying density is of what's going on. Okay, it completely fails to tell any story whatsoever. And that is the primary failing of that particular figure. Now, you may have noticed in the credits, that's a figure from one of my papers. One thing that I will note is that a lot of the visualizations that we'll be looking at throughout the course of this talk are my own. And the primary reason for that is it's much easier for me to be highly critical of work that I have done in the past than, say, some random figure that we find on the internet or in some other paper. This is not because I am perfect at visualization. In fact, I think the previous example clearly demonstrates that I have made many mistakes in my past. But I do find it instructive to go back to my old papers and look at figures that I have made, perhaps years later, or for me now, decades later, and ask myself, what is useful about this figure? What is not useful? What is effective? Right? And that is something that we can all do. You can all go back and look at previous visualizations and understand what worked, what didn't, and how does that inform anything that you're going to make in papers moving forward. Okay, so no story at all. No story told by that figure. All right, another lesson from that problem is that captions matter. So there was a color bar, there were a whole bunch of symbols, there were a bunch of dashed lines that had numbers next to them, okay? But none of that was defined by the figure itself. And so captions are a critical part of telling the story of a visualization. This is something we will also talk about in greater detail throughout the course of this week. But one thing I want to do before we talk more about captions and how important they are to framing and explaining what is happening in a visualization is to issue a challenge to each of you. And that challenge is that I would like for you to strive to build visualizations that do not require captions. Okay. That is very difficult. I'm not going to claim that it's easy, but it is also not impossible. So I think that that is a meaningful and useful goal for all of you to take away from this lecture and this session. Okay. So, what? Adam, slow down. What if my figure, my visualization is just a histogram? So if all you have is just a histogram, okay, that fails to actually tell a story of any kind, then I contend that it shouldn't be a figure. Right? So histograms are often used for things like showing a mean or a median or the variance of a data distribution, and those can easily be summarized in a table. If you just want to talk about the distribution itself, like this is something that is multimodal or it has some long tail extending out to infinity, again, those can be easily described in a single sentence of text. So if the figure itself is not going to tell a story, it doesn't need to be a figure. Now, there may be some gray area. Sometimes you feel compelled that you have to show the histogram or you have to show the data, but it's not necessarily telling a very important story. In a paper, what I do in those situations is move that sort of thing to an appendix. And people that feel like they must look at some sort of weak narrative figure, they can do that if they go all the way to the appendix of the paper. But just a histogram that tells no story is not something that we should be putting into our talks, into our papers, into presentations that we share with other people. Okay. So I now want to spend a bit of time talking about effective communication. And in particular, how do we build effective communication as part of constructing visualizations? So to build very effective visuals, I think that you should ask yourself the following 3 questions. Okay. What is the fundamental purpose of this figure? So if you're building a figure that's going to go into a paper, there should be some sort of big idea. And I want you to work on thinking about and capturing that big idea. There can be little ideas that are also teased out of any individual visualization, but we want to make sure the big ideas are front and center. The second question is, if this visualization were in the newspaper, what would the accompanying headline be? Right? So imagine that every single thing that you work on is actually a news story. And asking this question about the headline of your figure, will help you get back towards the fundamental purpose or the big idea. And the third question I want you to ask yourself is, will other people see this visualization, whether it's a plot in my talk or it's a plot in one of my papers, and try to steal it for their own talks, right? And that, I think, is a sign of a great visualization. Essentially, people are going to take plots from other people's work when they do a good job of communicating, right? If there's something that my own figures or my own papers don't quickly address, I'm going to take a visual from somewhere else that does that really well. And this is why, for instance, artist renditions of various phenomena that happen, say, at places like NASA to accompany press releases and things like that, those show up again and again and again in talks, because those are incredibly effective visual forms of communication. You can often look at those types of things and immediately say, oh, okay, I know what's going on now with this system. Okay, so consider the following figure. All right, so let's ask about this figure that is in a previous publication of mine. Let's ask ourselves the three questions that I just posed to you. All right, so what is the purpose of this figure? Honestly, 5 years later, I'm looking at it, I don't know. Maybe it's a Rorschach test. Maybe you see what you want to see in this particular figure. If I were to apply a headline to that figure, I would go with something like, local astronomer fails to communicate anything of particular relevance, right? We just basically have a bunch of plots on a bunch of different axes without a whole lot of information about what's important about what you're looking at, right? Okay, so let's ask, would somebody steal this figure and use it themselves? To that, I do think the answer is yes, but only if the figure was printed on a piece of paper and the person needed to start a fire. Okay? In other words, that was a very poor visualization. There's just nothing that's really jumping out as telling us why this is important and why there's information that you must glean from what is being shown. Okay? Alternatively, let's consider this figure. I'll give you a second to take a look at it. Okay. So I see here just a few data points. I see well-labeled axes. Let's ask the three questions about this particular figure. Okay. So what is its purpose? It shows the cosmic star formation rate as a function of time. If you were to come up with a headline for this figure, I actually think that there's many that would be appropriate, all of which sort of tell the story of this figure. But the thing that jumps out to me for this particular plot is that something like, universe forms fewer and fewer stars with every passing year. Okay? And would people want to steal this figure? Yes. Literally 10,000 times over, yes. So this plot, let's take another look at it. This plot is now known as the infamous Maddow plot, and it is based on essentially measurements of the star formation rate as a function of redshift, or other versions are as a function of look-back time. And this is work that was initially done by Piero Maddow and collaborators. Okay? And when I look at this plot, I find myself marveling at its simplicity. So in this case, there's been some binning of the data, so there's only 7 data points, but we can see very clearly what the story is here. The star formation rate at a redshift of 0 is much lower than the star formation rate was at a redshift of 1, which is roughly, in the history of the universe, as far as we can tell, when the star formation rate peaked. Okay? And so shortly after the start of the universe, at very high redshifts, the star formation rate is increasing, and then it hits some peak at redshift 1, and then begins decreasing. Okay? There are 3 different symbols here, okay? And those have to do with different measurement methods. I happen to know that because I'm an astronomer, but I never even read the caption, right? I can just look at this and I can tell why there are different symbols in this figure and what they mean. There's no effort to add a lot of sort of snazzy color or anything like that that's jumping off the page. This is just a very simple plot that effectively tells the story of how star formation has evolved on a cosmic scale from the start of the universe to now. So, all of us should strive to one day make a plot that will be named for us. Okay. So, that is the second challenge that I want to issue to you today. Build visualizations that other astronomers simply have no choice but to steal from you and put into their own presentations and talks. Okay, so why visualization? We are a program that emphasizes teaching data science, and indeed we have many sessions devoted to the different topics and analysis techniques that fall under the umbrella of data science. So why is visualization something that we include as part of this program? And the reason is that data and analysis, in my opinion, are worthless if the results of the analysis of the data cannot be communicated to other people. So within the whole scientific community, the obtaining of results that have not been communicated to others is essentially a failing of science itself. Okay. To borrow a trope, if we are working towards communication, a picture is worth 1,000 words. Okay. All that being said, for everything that we do in the DSFP, visualization is particularly difficult to build instruction around. And that is because there is no right answer. Whereas we might build a machine learning model and it is able to correctly classify 87% of all the results, and that's sort of the optimal machine learning model that you can build. Or you might be able to do some inference on some data and measure the value of the speed of light using something like a Bayesian MCMC model. Visualization has no right answer. And the reason for that is that every person, right, every viewer of a piece of visualization that is created is going to bring their own personal history and perspective to what they are seeing. And unfortunately, you cannot perfectly know what that is for every individual in order to craft a figure or a plot or a slide that perfectly matches what they are going to see. So here's breakout problem number 2. I'm showing a histogram of the number of transients that are discovered as a function of time. Okay. So the question is the number of transients increasing or decreasing with time? I'll give you a second to think about it. Okay. I assume at this point you probably have an answer. You probably said decreasing, but maybe not. But honestly, either way, the fact that this is actually a question where you have to think about what the answer is a real problem. I'm again showing the exact same figure, but in this case I've added a bit more ink. In particular, I've labeled the y-axis, and I've also labeled the data. So here's what's so misleading about what was shown a second ago. The reason I said that you probably said decreasing is that we are all accustomed to seeing histograms with positive numbers that go up. And so in this particular figure, that looks like then the white portion is the data, right? That is the bars that are going up. But instead, this unusual choice has been made to show numbers that are increasing going down. Okay. Now, if you label the data and you label the axes, it's clear that the number of supernovae and transients that are being discovered is increasing as a function of time. But that's totally counter to what all of us would naturally expect when looking at something like a bar chart or a histogram. In this case, I have intentionally subverted your expectations. Once there is an axis label, it's not too difficult to see what's going on. But we all naturally, as I said, expect the bar chart to point up, right? Which is why it looks like the white portion is the actual data when it is not. Okay. The reason I bring this up is that even though we cannot perfectly solve for everyone's personal history and how they're going to perceive an individual visualization, we can use a viewer's expectations to reduce their cognitive load. So if viewers are used to looking at figures of a particular type, building figures that are familiar or in a familiar style will make it easier for them to quickly process what they are seeing and then return to whatever the next task is. So if they're reading your paper, the next task will be reading more text. If you're giving a talk, the next task will be listening to what you are saying. Because if someone is looking at your figure and trying to understand what's happening within the figure, they are not listening to the words that you are saying. Okay, I'm I'm also going to take just a brief moment right now for a short aside. So in addition to an individual's personal perspective, which we've said several times now is impossible to know. You can't know exactly how someone is going to respond to a visualization. Visualizations can also have a physical perspective. And this is something that particularly comes up when dealing with multidimensional data sets. Now, as astronomers, almost every data set that we ever deal with has many, many dimensions. If you're working with Rubin Observatory data, we actually will have, for every individual source that you care about, its location in 3D. So we'll have a position, an RA, and a deck on the sky, and then we'll also be able to measure photometric redshifts, which will give us a distance. So we'll have positions for these things in 3D, but the data set will be even more dimensional than that. We'll have colors for these things. We'll have models that can infer things like masses or star formation rates based on the colors, metallicities, age, etc. So we work in multidimensional data sets within astronomy. Okay. So in some cases, we need to consider physical perspective. So that brings us to breakout problem number 3. So this is a short one again. My question to you is, what is this? All right, so I'll stop there. This looks like what? I don't know. This could be a new design for a building in some downtown city center, like a twin set of buildings or something like that. That's very modern because it's not perfectly the same size everywhere. I don't know. But let's talk for just a second about the perspective here. So we've created a 3D visualization for this 3D data set. And part of the problem here, as I said with perspective, is that everything that's happening in the top corner of this image is completely obscured, right? So we have a lot of data that's sort of jutting out of the bottom plane, which typically we would call the XY plane. But that data itself obscures whatever's happening at different locations in XY. So that's like a real challenge if you're dealing with 3D data. And that's something that never goes away if you're dealing with 3D representations of data. Okay. For this particular data set, the answer, what are we looking at, is actually quite obvious, but you can't really tell it from the previous visualization. Let me show it in a slightly different method. Okay, this is the exact same data shown in 2 dimensions with a little bit more intelligent choices in what's being visualized. And clearly, what you now see is a figure 8, right? This is a pixelated scan of a handwritten number 8 digit, and the data set itself lives in 3 dimensions. So every pixel has a coordinate, x and y, and then there's some intensity associated with that pixel regarding for how much ink essentially falls within an individual pixel from the scan of the handwritten digit. Okay. As I said before, 3D representations, even though this is a 3-dimensional data set, totally obscures the simple to interpret and familiar form of this number 8. Okay. So the second representation of the data here is a very good example where less is more. And that's another thing to keep in the back of your mind as we go through the course of this week studying data visualization. Less is very often more. Visualization tools like Matplotlib make it very, very easy to add, right? You can Google Matplotlib, add color, Matplotlib, color axis, Matplotlib, large font, Matplotlib, curly arrows. You can add all kinds of things. There's almost no end to the features that you can add to some sort of plot that you've created with Matplotlib. Okay. And despite the fact that it's very easy to add all of these different bells and whistles, as more and more information is being layered onto individual visualizations, that increases the cognitive load of your audience. And to the extent that it's possible, you always want to minimize the cognitive load while still managing to tell a good story. If you think back to the very first plot that we looked at, the very first example shown as part of this talk, right? There were all kinds of symbols. They were layered on top of each other. There were different colors. There were different symbols, but it was hard to tell because almost all that you could see was X's at the very top layer of everything that's been layered. There was also these dashed lines and a bunch of numbers, right? That's a lot of information, a lot that's being layered, and yet no obvious explanation as to what information within that data set is particularly important to the audience. Okay. So, a good maxim as you're building a visualization is to avoid high ink to information ratios. So if adding something requires a lot of ink without really doing a whole lot in service of telling your story, it's something that should be avoided in your figures. Okay. Furthermore, 3D representations should be limited to data sets that are physically three-dimensional. And so what I mean by that is if you have like particles that are moving through space, that is something that is three-dimensional and so is a worthwhile 3D data set. If you have a bunch of different measurements of the same galaxies, say the mass, the metallicity, and the star formation rate, those things are not physically in 3D, and so they would be much better served being represented in 2 dimensions. Okay. So, as practicing astronomers, essentially you should never be thinking about building a 3D visualization unless you're showing something that is physically moving or exists physically within space. Okay. Now, as astronomers, that means we get to break this rule a decent amount, much more so than, say, other fields. But we're going to spend a lot of time, actually, talking about 3D visualization in another lecture that's going to happen later this week. So I'm not going to sit on this point and continue to harp on it for much longer. But in most cases, you can communicate perfectly well in 2 dimensions rather than 3. And that ends my aside. Okay. So, while we do not perfectly understand any individual's perspective, there is a lot that we know about human cognition, right? And as one example that's come up in previous talks at the DSFP, we can immediately look at, say, 2 lines that are next to each other and tell which line is longer, which line is shorter. Okay? But we have a lot of trouble telling relative color differences, right? Is this thing cyan and this thing turquoise, or vice versa? That's very challenging. And so if we can build visualizations that use the fact that humans can perceive some things easier than others, we can tell better stories, right? Again, by reducing cognitive load. We'll talk about this more in talks later this week, right? But we want to leverage, right, these differences in human cognition, things that are easy to quickly interpret, things that are challenging to interpret, to maximum effect. We want to make sure that we always make things as easy as possible for our audience. Okay. So that brings me to sort of the big point for today's lecture and where we started with the title, and that is salience. So we have emphasized a lot simplicity, and we've emphasized efficiency as key components in building effective visuals that communicate whatever information you want to communicate. And so now I want to introduce the idea of salience. So good visualizations facilitate the immediate identification of the most important feature in a figure. So whatever is the most important thing should be immediately seen in a good visualization. Okay? And this happens when those important features are salient. So this is what we mean by building salience in your visualizations. Okay? By leveraging standard human cognition, okay, and a few principles like similarity, proximity, connection, and enclosure, we can rapidly communicate the most salient features of a figure. Okay? So now we'll look at examples, again, using work that I have done in the past. So similarity. In short, objects that have a similar appearance are naturally going to be grouped together by a viewer. Okay? So here we see a plot of a supernova light curve. And this is essentially the brightness of this supernova as a function of time in a bunch of different astronomical filters. So what is the similarity that's happening here? Observations that have been obtained in the near infrared are all shown as pentagons, and they're all shown with sort of reddish or brownish hues. Whereas observations that are obtained in the ultraviolet are all being shown as hexagons that are shown as sort of bluer hues, right? And we know that the UV is typically used to observe things that are hot, and things that are hot are blue. So we have a nice sort of semantic match here. And we also have a nice semantic match. Things that are cool, which are observed in the near infrared, tend to be more redder in appearance. And so we have that nice semantic match as well. Now, if we're also going to be a bit critical of this figure, we have really, really poor visual boundaries. So we have symbols that are supposed to be contrasting, and yet a pentagon and a hexagon do not look all that different, especially if you're only looking very quickly. And then finally, the big criticism of this figure is that it does not tell any story whatsoever. This one, again, is like, I don't know why I put this in the paper. I can't tell you now, a few years later. It's not something that's interesting, frankly. Basically, the supernova got brighter, it went up, then it got fainter, it went down. It did what all supernovae do. But there's no other story, really, being told by this particular figure. Okay. Proximity. Objects that have small separations or things that are very close together are naturally going to be grouped together. So here's an example from the paper I actually mentioned earlier, where I was trying to classify stars in astronomical images. And you can see here sort of a gallery of example images of stars and galaxies. And you can see that the separation between the individual stars is much smaller than the separation between the stars and the galaxies. Right? And so this is what I mean by proximity. We've separated the galaxies and the stars so that you naturally group the stars as you run along the row together, and you naturally group the galaxies as you run along the top row together. Okay? We also have proximity in the sense that along the columns, we have the brightest objects on the left at 16th magnitude and the faintest objects on the right at 22nd magnitude. Okay? Now, if we're going to be critical, if you actually go to the paper, this figure does not actually have as wide a separation between the stars and the galaxies as what's being displayed right here. And that actually is not a good thing. Basically, we're treating all these things as being proximate or close together, when in fact, the stars and the galaxies are quite different in their nature. Okay, connection. This one is very straightforward, but objects that are connected are naturally grouped together. So here we have a bunch of observations of a special class of type 1a supernovae. So essentially these are intrinsically faint and fast declining type 1a supernovae. And we have measurements that have been made in the R band and the G band, which correspond to the red and the green symbols respectively. And we're using dashed lines to connect the R and the G band observations. So you can immediately tell, okay, this is the value for this supernova in the R band, this is the value in the G band. Okay. What else is good about this figure? The paper itself is about a supernova called IPTF 16FNM, and we've used the special star symbol. So a thing to remember is that the star symbol is always going to grab a reader's attention as being more important than anything else that's being shown. So we use that special star symbol for highlighting the supernova that the paper is about. Okay? What are some not so great things about this figure? Well, all of the symbols otherwise are identical. The only way that we're drawing a visual boundary between them is from the color. And color, as we've said, is not a great indicator of differences between objects. And in black and white, or for someone that's colorblind, that may not be very good. So instead, if I were to remake this figure, I would use much stronger visual boundaries to differentiate between the R band and the G band, so that if color is there, the color is secondary. It's not the primary way that you would tell the difference between these particular symbols. And then finally, of these principles that I discussed, enclosure is the last one. And objects that are enclosed are naturally grouped together. So if you want to, just a quick hint, if you want to build salience, there's nothing you can do better than to enclose some object, right? Let's think back to the visualization from the preamble where I was showing Supernova 2007 UI, and to highlight the position of the supernova in both the optical and the X-ray images, I just dropped a circle down, highlighting where that thing was, right? I basically enclosed the optical and the X-ray, and it was immediately obvious then what was the X-ray source that corresponded to the optical source. It was also immediately obvious that that was the most important thing in that visualization. All right, so here's a paper about a decade old now, where I have enclosed a bunch of special stars relative to a large sample of stars that were observed in the time domain. And so you can quickly see, okay, what's the most important thing in this figure? It's going to be the stuff that's happening inside, or potentially conversely outside, of the regions enclosed by the dashed blue and red lines. This, again, I'm looking at this and my eyes, once again, they hurt. It's not always easy going back and looking at your old papers because sometimes, well, you've done things that aren't so great. But there's several problems here. It probably would have been better to use contours than just slapping all these data points on top of each other. The color choices are a bit bizarre and not helpful. Again, the special star symbol is used appropriately. It's highlighting newly discovered Arcor-Bohr stars, which is important, but this is not easily telling an important story to the reader. The caption helps, but it's not a great story. This could be improved in many ways were I to redo this figure today. Okay. So one other point in closing here. When building salience, things that stand out are easy to find. So here's a recent paper, a figure from a recent paper that I wrote, and I actually think that this is on the verge of being a perfect visualization in the sense that it is simple and it is effective, and you might want to make some minor aesthetic changes, but otherwise this clearly tells a story, right? So what do we see here? We have, again, a light curve. We have brightness as a function of time. We have a bunch of brightnesses in the G band labeled GZTF here, and in the R band labeled RZTF. And we can see a whole bunch of points, right? What are all those points? That's a bunch of normal type 1a supernovae. And then we see the observations for this new supernova, the object of this particular paper, which has been highlighted here in green and in red. And in the green and in the red, we're using different symbols, so it's very clear which one corresponds to G and which one corresponds to R. And then we see also, right, the use of the open circle, which is arguably the perfect symbol. The perfect symbol because as open circles overlap, they don't create other shapes that are similar to a circle. So you get a very good sense of what the density is, the underlying density of the distribution. But here immediately, right, what is the story? The story is that this new supernova is fainter than all the other supernovae that you see. This new supernova has a decline rate that is faster than all the other supernovae you see. And this new supernova lacks in the R band a feature that you see in most of these supernova, which is sort of a secondary maximum or a bump that happens about 3 weeks after the time of maximum light, right? And all of those things, I contend, are immediately clear from this figure. You don't need to spend a lot of time looking at it to understand what is going on in this case, okay? And that is because the supernova that I care about and the one that I want to draw your attention to stands out, and it is very easy to find in the crowd, okay? It is exceptionally salient. So that brings me to my conclusions for today's talk, right? Visualization is an essential tool in the data science toolbox. As our data sets become larger and larger and larger, we need to figure out effective ways to communicate what we're learning about those data sets, for which visualization is essential. But we also get to the point where our data sets become so large, we may not actually know what's interesting within the data or what we should be looking for within the data. And visualization can be a very useful tool for teasing out that information as well. Science communication hinges on effective visualizations. Imagine for a moment trying to go to a talk or a lecture or reading a paper that has no figures. I'm kind of scared by that thought, and you should be too, right? With no figures, with no visualizations, it is very difficult to fully understand all of the work that a person has done. Okay? As you are building visualizations, this week, we all implore you to tell a story. And I specifically ask you, as you tell that story with your visualization, to try to build a figure, try to build a slide that other people are going to want to steal, right? If you are building very effective communication, very effective visuals, that is going to be something that everybody else is going to want to take and put into their own talks because it's going to make their talks better. So that should be what you strive for. And that's not like a one figure per paper thing. That is what I try to think about for every figure that I create. Am I successful every single time? No, absolutely not. No one will be. There's no way that every single figure you create and every paper you write is going to be used by someone else in a talk somewhere. But it's something you should think about because it's going to allow you to make better visualizations. Okay? And finally, before we jump into the notebook and start working on the problems associated with this lecture, I just want to remind you that focusing on the salient features allows you to accomplish all of the different goals that we talked about today. Right? The salient features go back to what is the purpose of this figure. The salient features inform what is going to be the newspaper headline. The salient features, if they are appropriately highlighted, will create effective visualization that then makes other people want to steal your figures. So every visualization that you make, figure out what are the salient features and how you highlight those in service of telling your story. Okay, great. Thank you. That's all I have today. And with that, let's jump on into the notebook and work on building salience within Matplotlib.